Greetings, everyone. I want to go over the next quiz that's on separating variables. There are two sections that apply, 2.2 and 2.4, although most likely it's more something from 2.4. It's an application of separating variables. And so what I will, again, remember this is a review, and I will propose the problem, and the best thing for you to do is actively use this video by pausing it and trying to solve it yourself, and then looking at the solution, comparing it with what you did, and see where your mistakes were, or if any. So use this wisely, these review videos, and also be careful. It's just not because I do one particular type of differential equation that doesn't mean that that's going to be the only one that's going to be on the quiz. It might be something from the same section, from the same topic, but in different form. Okay, so I want to go over one problem here, and I'll take the opportunity also to discuss something that we had seen in the introduction of an application of these differential equation. And this was, I remind you, so this, what I'm now saying is not really part of the quiz, but just to remind you that we have the Verhulst model for population growth. Whoa, what is going on here? For population growth. Okay, and I just want to give I'm going to do a concrete example. Not really. I mean, if you were to do this in real life, the numbers are very ugly. So I'm going to take something rather simple. Let's look at the following equation. Here is the equation: y prime equals. So what was the model? It says that the rate of change of the population. So normally we would write a p here, but I don't want to confuse you, so I'm going to write the y here. Y times 1 minus a constant times y, and the constant I'm going to use is 1000 y. There's a reason that I use this particular constant. You might say, oh, this is ugly, but if I don't do this, then it's a word, it has no bearing at all. So now at least it has some bearing to a real problem. And I'll make it an initial value problem, and I say, suppose that the initial population, so at time, of course here this is time t, right? That it was 100 people, or 100 members. So that's the initial condition, so find the general solution. Of course, I could also ask, so what happened after, let's say, time is measured in years, after 2 years, what happens after 10 years? Okay, these are the kind of questions you can ask. Very often I put them perhaps as an extra credit problem. The main thing, of course, is solving the differential equation. Now, as such, it might not immediately recognize what it is, so let's just work out all the terms here. Let's distribute. So we get this equation, and now you should recognize what type of equation that is. And that is, of course, the problem with this type of, for the quiz, is to recognize what type of equation do you have. Can we separate the variables here? Now remember, separating variables is not possible here if you think about it, because you have to have something that one single term on the left containing y prime and y, but there are two terms here, right? So what we see here is something of the form to write it in is this form, and then it is of this form: y prime plus px is equal fx y to the power r. This is what we call the Bernoulli form. It's a very special form. So you have to manipulate a little bit to see that it is actually in this form. So I just want to remind you, if there would be no r here, then we would be dealing with, oh, sorry, I forgot to write the y. I hope I said it, but I forgot to write the y. So if this is a general Bernoulli equation, if there would be no y here, if r is 0, then we would have a linear first order differential equation. But this power of y makes it no longer linear. Okay? And this is what we have here. We have the power is 2 here. Okay, so how did we solve this? So there were also several steps. Step 1 was, well, we use very often the same method always, the method variation of parameters. So we look for so-called the homogeneous one. Here, let's still call it a complementary, although it's perhaps not really the terminology that people would use. This would be just y prime minus y equals 0, right? So what is the solution to this thing? This by now we can do very quickly. So this is actually really separation by variables, right? This is this. If you want to, you can write it with infinitesimals, so that if you integrate, you get ln of y equals x plus a constant. I'm going to call this d because the next step I have to do is exponentiation. Then I get y equals e x plus d, and that we split that as e to the power d times e to x, and so this is cex. Okay, so I'm using x here, although in population I should use t. Okay, but let's just applications. We will do a once in a while applications, and then perhaps we should take the right variables. But I just put down the equation here. Okay, in the quiz I'm not going to do this kind of. I'm not going to worry about the exactly name that I gave to the variable here. Okay, so that's step one. But that is not how we solve this. This is just to set up our general solution is going to be of the form u times, and you choose one of these. So choose c equal to 1 here. And so we multiply this here. So this, I remind you, this ex, this is the homogeneous one. We're going to write it here. It's this one factor, and the other factor is this new function u, this parameter. Don't have to call it that way, but depending on x. Okay, and then what we do? Well, that's we take the derivative here. Y prime is the derivative of the first, copy the second, plus copy the first, take derivative of the second, sorry. And then you plug this into the original equation. This is our original equation. So we get u prime ex plus u ex minus y, which is u ex, equals a minus 1 over 1,000 y squared, but y squared is u squared e 2x. Okay, I have to square this thing, and squaring a power is the power of a power is the product of the exponents. Okay. All right, that's it. What we need to know, we need to some cancellation, and that's exactly what we see here. And if we do everything right, then we can separate the variables, and we see that we can bring. So separating the variables really means that there's one term on the left containing only u, and one term on the right containing only the variable, in this case x. So we do u prime over u squared equals, and so what we have over there, let's gather everything. We have a 1,000. We have an e to the 2x divided by e to the x. Now, again, we want to simplify these things. At some point, we're going to need to integrate things, so we don't want this to be as ugly as it is, right? And how do you simplify fractions? Is subtracting the exponent. So this is e to the x, okay? So if you bring this up, so this would be minus x here, and then that's where we get the e to the dx. Okay, so let's write this already with a negative power, and also I'm going to write the du here is minus 1,000 ex dx. Great, so now I can integrate, and this gives me u minus 1 over minus 1. This is just the regular power rule, and here we have 1,000 as a constant, and the antiderivative of ex is just ex plus a constant, and let's call it d again. Oh, no, sorry, in this case I can call it c. I'm not going to change it anymore. Now, what we need is, this is our solution, our general solution. So we're looking for the general solution here, and so that's why we keep the constant here. I know this is a little bit confusing. Sometimes we say, oh, we only want a particular solution, but in this case we want the general solution. Okay, so we keep the c, but we need u, and okay, so we have to solve this for u here. So let's first of all get rid of this negative sign. So this is 1 over u is equal to, and then bring the negative sign to the other side. So it goes 1,000 ex minus c, but that is also equal to plus c. Okay, so be careful. So what I did here is
So this was perhaps a C1 here, and then this becomes a plus C here. This is something that you don't need to do that, but it's just sometimes easier to have plus signs instead of negative signs. Okay, so but I hope you know, I did it, and when you do this yourself, make it somehow clear, okay, that this is a constant, but by multiplying everything with negative 1, it would become minus C1, and I don't want to write minus C1, so I write plus C. The idea is if C is a constant and minus C is a constant, so I can rename it. Okay, but that's not the issue. The issue is that I have U, so I have to take reciprocals of both sides. So, okay, in case, so take reciprocals, because I have to solve for U, right? Or cross multiply, or however you want, however floats your boat. And we get 1 over 1,000 EX plus C. So our solution, our general solution is that times EX, right? Remember, this is the formula. Okay, so we get an EX on the denominator too. EX over C plus 1 over 1,000 e to the x. And that's our general solution. So, and that's fine. But I want to show very often one wants to make it a little bit more compact by dividing top and bottom by EX. Again, that is not necessary, so I put it in parentheses, but so you can divide by EX. But of course, that means you have to divide everywhere by EX. And then the form becomes, it's a little bit more compact that way. It's 1 over 1,000, I'm going to write this first now, plus c to the e to the minus x. Because dividing by ex is multiplying with e to the minus x. Okay, so that is our general solution. I'm going to work with this one, but you can as well work with the original one. It really is not much of a difference. So step, well, what step we are? Step 3, might have been step 4 already. We need the initial condition. So for our initial condition, we take, if x is 0, then y was 100, right? So let's plug that in. So we plug this in here, we get 100 equals 1 over 1,000 plus, if I plug in 0 for x, then e to the 0 is 1. So I get just c here. Okay, again, taking reciprocals means that 1 over 100, or cross multiplying. Okay, let's go cross multiply. This is in this case perhaps easier. So, so I'm bringing this to the other side. So 100 times 1 over 1,000 plus c is 1. So that means sorry, yeah, okay, no, that's fine. Okay, so this is, there is actually a better form I realize now, is if I multiply top and bottom here with 1,000, then I get 1,000c and I rename that my new constant. Okay, but let's go on with the way, I didn't do this, so let's keep going here. So we get here 1 over 10 plus c equals 1, so we see that c is 1 minus 1, 10 is 9/10. Okay, so our solution is y equals 1 over 1,000 plus 9 over 10 e to the minus x. Okay, but again, I don't like much fractions, so I like to clear the denominators. Fraction in a fraction, I don't like that much. It's not necessary, but it is easy by how do you get rid of this? By multiplying top and bottom with 1,000. So I'm going to do this here. Multiply top and bottom with 1,000, so they get 1,000. So let me write that here. So I write 1,000 here, 1,000 here, 1,000 here. Of course, every single term has to be multiplied with 1,000, right? So I get 1,000 on the top, then I get 1 there, plus, what is this then? Well, 1,000 by 10 is 9, wait, oh, sorry. Oh no, the initial population was, yeah, 100. No, I'm right. So 1 plus 9. Sorry, I lost my track. 900 e to the minus x. Right. So if I plug in 0, let's see, I get. No. There's something wrong here. What did I wrong? Okay, I'm sorry, I got a little bit lost here in the calculation. 100. Oh, 100C here. Okay, I forgot to multiply here with C. Yeah, so was because I made my life hard by doing this. Okay, this calculation is correct, but let me show you why it is sometimes useful to simplify things before you start doing calculations. Okay, because I made a mistake. I didn't multiply something out here. So what I want to say is I can even simplify this further by multiplying top and bottom by 1,000. So I get C 1,000 E minus X. And then I say this is a new constant that I call K. Let's call it K now, because I don't want to 1 plus K e to the minus X. This is much simpler to deal with. So now I look at the initial condition. So the initial condition, if X is 0, then Y is a 100. So I get 100 is 1,000 divided by 1 plus K. Okay? So cross multiply, 1 plus K is equal to 1,000, divided by 100, which is 10. And therefore, K is equal to 9. So the solution that I have is Y equals 1,000 of 1 plus 9 e to the minus X. Okay. Okay. So one thing this ends the quiz, but since we are discussing this population thing, I want to show you a little bit more about it, give a bit more background. So extra. We know that in these models, what we often interested in, what happens in the limit if X goes to infinity. This population is growing, and where does it eventually end up? Does it peter down to nothing? Does it explode into infinity, or does it somehow stabilize? And if we take the limit, we discussed this also when in the introduction here. So what happens then? Well, the only thing that an infinity is plugged in is this here, and so e to the negative infinity would be 0, and so what we get is that the limit is actually 1,000 over 1, so exactly 1,000. So this model says that after long enough time, the population will be stabilized around 1,000. Okay, that when there's 1,000 of members in this population, then the rate of dying and the rate of birth are going to be equal. And so, for instance, let's see what happens. What happens if X is 2? Okay, now this one I need a calculator for, because I have to calculate now y of 2, and that means just plugging 2 in here, right? I'm going to plug in 2 in this equation, but I'm going to use a calculator for that. And so if I do that, I find approximately, so this is using a calculator, right? So perhaps I do it in green. So this is the calculator. Tells me it's approximately, this is allowed, by the way. You can use calculators at any time, right? This is approximately 450. So you see, we started with 100. We far away from the equilibrium of 1,000. But after 2 years, we're already halfway. What happens after 10 years? I'm thinking now of this in years, right? And I should have used t, but I'm using x. So what is y10 here? Y of 10, so let's calculate that. 10, sorry, give me, yep. And this comes out to be 999.5. In other words, after 10 years, we reached our maximum, our stable population. So you see that these models sometimes you can look this up. Go look up on Google, and if you Google these things for host models or certain things, and I found, for instance, in where a certain region in India, I think, or Pakistan, perhaps, I forget now where it was, that they calculated the constants,
used then the model and then predicted the population for the next 4 years, 5 years, and then later on checked it with the population, and it is almost correct. So these models are pretty correct at current, but not always. At some points, there are other elements that come in that do not take care of yet. The model is not still fine-tuned enough. But of course, this is not our concern. We are not dealing with this kind of problems. Okay, so that is one question, and I want to do perhaps very quickly, just so that we have something of each possibility that I would most likely going to ask is I want to do one of these, the other type, and the one I want to do is, let's do, looking for one here. So question number 2 would be, let's do y prime equals y squared plus 2xy divided by x squared. Now you could try to write this in this form here. So you should always try to write it in this form. See whether you get a Bernoulli. Of course, the general form is this way, right? This is our general first order differential equation looks like, and that is really in that form that we have written it. Is it of the Bernoulli type? You might be inclined to think, yes, it is, because if I bring the x squared to the other side, I have this y here, and y squared is exactly what we have here too, right? Y and a y cube, or in case y squared. But you have this x squared in front of your y prime, and so therefore you're not in standard form yet. So here it is a bit debatable what you could do. You could write it as this way. So you can treat this as a Bernoulli. As if you, now, in other words, first thing we do is we have to divide everything out. And then you could say, okay, I can write this, if I bring this guy over to that side, I am in a Bernoulli form. So you can use the Bernoulli form here. So this is potentially Bernoulli. This is Bernoulli. So you can do the same thing. But it is easier to see here, it's quicker if you realize, oh, but this is also of the form that the book's called homogeneous. It's nothing to do with homogeneous from before. So it is a function in y over x, right? If I simplify everything, this is y over x squared plus 2y over x. I'm canceling one of the x's here. And this now is much easier to see that we know what the technique is. So for something like this, the step 1 is simply, well, you take y equal to, you basically take y over x, you call that a new function, u. Okay, this is what you do here. So you replace the y over x by u, of course, u depending on x. So we get y prime is u squared plus 2u. And of course, now what you get is actually here a Bernoulli. So you now can do the Bernoulli thing. Oh, no, sorry. No, I apologize, sorry about that. I shouldn't. I went too fast, right? Because this is not y prime. What is y prime now? I have to write y prime. Y is ux. So what is y prime now? So, okay, the right-hand side is correct, but what y prime is, let me do it here first. That is u prime x plus u. That's the product rule. So here we get u prime x plus u. Okay, so now I have to bring, there's no cancellation necessarily. That this is the type of thing where this kind of cancellations might not happen. So we get u squared plus u. Okay, but this is separating by variables because there is no x's on the right hand side where they should be, but therefore I can divide it out. So I get u prime over u squared plus u equals 1 over x. I bring the x to one side and the u's to the other side. Remember, if you have a differential equation of this form that can be written in terms, so let me write it up here, in terms of y over x, then using this substitution, if you want, you will get a separated variable, a separated equation. Okay, so we have to integrate this. That is du over u squared plus u equals dx over x. Now, how do you integrate this left-hand side here? The right-hand side is easy, so I'm going to write it ln x plus c plus d. Let's call it d because we're probably going to have to do something here.
How do we do with this right-hand side? Well, this is a function, a partial fraction, right? We have here 1 over u squared plus u. Now we know how is a partial fraction. So partial fraction, I haven't yet done one in full detail, so let me do it here now. U squared plus u equals 0. You factor the denominator, that is u times u plus 1. And then you know that the partial fraction exists with these two so u equals 0 and u plus 1 as denominators. And the numerators are some numbers a and b that we need to determine. How do we determine them? Well, so this is the proposed partial fraction. So this is the proposed partial fraction. What we need to do is find a and b. So find a and b, and there are unique numbers. Okay, so first thing we do is of course cross multiply, get rid of the denominators. So we multiply everything with u squared plus u. Oops, plus what happened here? U squared plus u. Here we do u. Why is it jumping? U times. I'm sorry. Sometimes this acts up. This thing. Jesus, what is going on here? Okay, let me go out of there and come back in, because that is the only way that I can get rid of this. Okay, u times u plus 1 and u times u plus 1. So we get 1 on the left hand side. Let's go in black. 1. And then here we get the u's cancel. So get a times u plus 1. And here the u plus 1's cancel, pu. Now there are several techniques. Some people say expand and compare coefficients. But there are in these cases, there are simpler things. So plug in special values. So plug in, and the special values that are the roots here. In this case, it's very easy to plug in u equals 0. If I plug that in, I find that 1 is equal to a plus b times 0. So I know already that a is 1. The other root is u equals negative 1. If I plug it in, the first term, this one is gone, right? So we have only this one to deal with. So we find that 1 is minus b. Okay, u is minus 1. So we have everything. So what we see is that this partial fraction is the same as the integral of 1 over u minus 1 over u plus 1. And you can always quickly double check that this is what it's supposed to be. Just put it back in common denominator and verify this is what you need there. Okay, so we have to integrate this. We can integrate each separately. And so that is both ln's, right? ln minus ln of u plus 1 here, absolute values or not. Let's not bother too much about that. Now, we want to put this in a one. Remember, we have to solve for u. So I'm going to have to do some manipulation here. And that is why you need to sometimes know how to simplify. The thing with ln's is that the difference is a quotient, comes from the ln of quotient. Okay, so let's write down what we have now. The ln of u over u plus 1 is the same as, and we had this one here, the ln of x plus d. Okay, we have to solve for u, so we exponentiate. We get u over u plus 1 equals e ln x plus d. And this one, again, we do e to the d times e ln x. Of course, these two the e and the ln x cancel, and e to the d I just call a new constant. So I get this. So this is a new constant c here. All right. Now it's still not solved for u. So still a little bit multiplication here. U is cxu plus 1. That is cxu plus cx. Yeah, these things tend to be a little bit long, a little bit of work to do. So we have to solve for u, bring this to the other side, this term. So we get u minus cxu equals cx. Factor out to u. 1 minus cx is cx. And then finally, u is cx over 1 minus cx. And that is u. Be careful. So last step, the solution. Oh, I don't know where. I forgot the numbering of my steps. So the next step is the solution is y equals this time. Remember, we have here, where is it here? We do this substitution, or rather this one. It's easier to work with that one. So y is u times x. So that is cx squared 1 minus cx. And then we could have an initial value problem that determines what C would be. So for instance, I'm not going to do this here, okay? And so that you could determine C. If I ask this, sometimes I might not ask this, and so. And again, another thing you can always do is now take the derivative of this thing and plug it in the original equation and see that that's what you get. That's a little bit of work, but that's a way of finding out whether you made mistakes or not. Okay, so I gave you an example of one of the two types that I'm going to ask you to do. And okay, so again, I have to remind you perhaps in the beginning of the course, and hopefully you get to this practice, show all details of your steps, like the way that I'm doing, okay? Sometimes, of course, I mean, if you would skip from this step to that step, that's not something I'm going to say, oh my God, this is, you copied this. No, this is okay. This is some steps go quicker, right? But if you would all of a sudden, out of nowhere, write down this equation, I would say, where on earth did you get this from? So I need to see where you get this from for me to be sure that it's you who derived this, okay? And you don't try to cheat. Remember, that is just my. I want to verify your honesty, but my assumption is that I trust you. You have signed this underpledge, so I trust your honesty. The only thing is, please do not abuse my trust, right? And if I would find then that you abuse your trust, and I want to remind you, I've told this before in the introduction, so there are ways that you can cheat by going online. There are even tutor sessions where you could ask this question and they will solve it for you, even with all the steps. But those things I can find out very easily too. For one thing, it's easy to recognize that somebody is doing that. I won't tell you all the details of it, because otherwise you might try to adjust for that. I really don't want you to try to cheat. But I wanted to warn you that in the past, people have tried to cheat, and each time I found it right away. And I gave a stern warning then, but only one. You get one warning, and if it's egregious cheating, then I might even say, okay, listen, you broke your honor code, that it invalidates your right to be in this course. Okay, take this serious, please. You're trying to learn something, and the only way you learn something is by able to do this, right? When you get a certificate that you have finished a degree at CityTech, and one of the courses was 2680 differential equations, your employer wants to make sure that you actually know how to solve differential equations. Okay, I don't want to lecture too much. I hope you also enjoy the working out and don't get freaked out by the length of these things. Now, perhaps one last thing. It is so easy to make mistakes, and I constantly do it, right? You see me constantly make mistakes. Sometimes I recover. Sometimes I might even have not seen the mistake and telling you, no, this is the solution, and actually it's different. But so that's okay. That kind of mistakes, I will penalize not that much. If it's just a calculation error, you might lose 1 point. But if then from then onwards you calculated everything correctly, you made a mistake and you now have something wrong. But as long as your steps from then onwards are correct, apply to the wrong thing, but then you get full credit for that. Okay? So making a mistake, that doesn't cost you that much, unless it's a major mistake, of course. But if it's just a simple calculation mistake, that shouldn't cost you too much. Skipping a step, that's going to cost you a lot. So understand how I grade, and also then why sometimes you might have less than you think you have, because you will look at the at the solutions of this quiz, and then you will say, wait, how come I have the answer, how come I have so little points? Most likely because you didn't show me all the steps. Okay? All right.